And we are going to present the work we've been doing with Fair-OBNC. So first of all, today we are focusing on the problem of label noise, which highly impacts not only the quality, but also the fairness of the models we are creating when data has incorrectly labeled instances. So what happens is that sometimes not only is labeling very expensive, sometimes it's impossible to know the correct labels. Also, if we have previously incorrect data and we train models with that, the decisions are going to be biased by that data. Sometimes we don't even know the real labels because the decisions are going to impact if we even know the actual outcome. And one example of this is the COMPAS case, for example, where we have this risk assessment software that determines if a person gets to live with a bail or not. So if we deny bail to someone, we never know if they actually have a high risk or not of recidivism because they are going to jail. So not only, and this case is even worse because black offenders are way more likely to be denied bail than white offenders. So this the misclassified labels are going to be much more higher in that part of the population. And so the model is just propagating the bias that already existed. We have more noisy labels on one part of the population. It's a big issue. We don't really have that great solutions for this. We can remove the instances that we don't know the label of. We can use the prediction as a label, but that is going to propagate the bias that was in the data that trained the model. So the goal with our work is to apply noise correction techniques to identify the wrong labels and to correct them. And specifically, we want to modify these noise correction methods so that we are taking fairness into account when correcting the labels. The other goal is to benchmark the method we created against other pre-processing fair machine learning techniques and also evaluate all of these techniques under different scenarios of label noise. Getting into the method itself, it was inspired by this noise correction method, which is ordering-based noise correction. And it works based on the concept of ensemble margins. So an ensemble margin is basically a measure of how sure an ensemble classifier is of its prediction. So if we give the features to an ensemble classifier, each of the individual classifiers is going to output a prediction. And then the final prediction of the ensemble is going to be based on the votes of each classifier. So we can calculate its ensemble margin based on this votes and know a measure of how sure the classifier is. So if most of the individual classifiers in the ensemble agree on the same label, it is probably very sure that that is the prediction. This is one formula for calculating the ensemble margin, where we take the votes for the true class and the votes for the wrong class. And if most of the classifiers are aligned on the original label, it's going to have an ensemble margin that's close to 1. If most of the classifiers are agreeing on the other label, it's going to have a value close to -1. This is one way of calculating the ensemble margin. For example, we have here a different one. This is more of an unsupervised way where we only look at the majority votes versus minority votes. So basically the absolute value of the ensemble margin is higher if more of the individual classifiers agree on the same label. So for noise correction, we can use this as a measure of how likely an instance is of being noisy. The intuition behind this method is that if we train an ensemble classifier to make predictions on the data, for the instances that it misclassifies, we can look at their ensemble margin, and if a lot of the individual classifiers agree on a label that's different from the one that's in the original dataset, we can more, with a higher probability, assume that that label is maybe noisy and we can correct it. So we can then, the way this method works is that it basically orders these misclassified instances according to this margin, and then the user can define how many instances they want to correct, and those are the ones that get flipped. In a diagram, this is what happens in the method. We have the noisy data, we train the ensemble classifier, we determine which instances were misclassified by the ensemble, compute their margins, and correct the top K most likely to be misclassified. what we did was modify certain parts of this method to also optimize for fairness in this process of correcting the labels. So the first modification that we introduced is takes into account the notion of demographic parity. So demographic parity is achieved when the probability of a decision is independent of the sensitive attribute. So for both sensitive groups, the likelihood of an instance belonging to a certain class is the same. So what we do is that we not only look at the instances in order by their margin, but we also only correct the instances whose correction is going to contribute to achieving demographic parity. So we are always aiming with the corrections to reduce the disparity of prevalence between the sensitive groups. For example, if we consider this case, we have, let's say, the ordered list of the misclassified instances with their margins, and we want to correct, say, 2 instances. If we apply the original OBNC method, it is simply going to correct the top 2 ones. But if we are trying to optimize for demographic parity, on the second row, for example, we can see that we have an instance of the negative sensitive group, and in this case, we are assuming that the positive sensitive group has a higher prevalence than the negative sensitive group. So on that second case, if we flip the label of an instance of the negative group from the positive class to the negative, the disparity between both groups is going to get larger, and we don't want that. So we basically still iterate the instances according to their margin, but we only correct the ones that contribute to reducing the disparities between the groups. This also meant that we changed the stopping criteria for the correction algorithm. So instead of simply selecting a number k of instances to correct, which is a bad heuristic because many times we don't even know the amount of noise that is present in the data set. So attributing a value to the number of instances to correct is not a very good stopping criteria. So we defined 3 criteria. The first one is a maximum flip rate. So we still define a max percentage of instances that the method can correct so that it simply does not flip the entire data set. We also determine a margin threshold so that it doesn't correct the instances whose margin is very close to the decision boundary. So that's going to be margins where the method, going to be instances where the ensemble is not that sure of its own prediction. So that's why we define a margin threshold, and we also define a disparity threshold. So if we are correcting the instances, if at a certain point the groups are already, the prevalences are already close to being equal, we also stop the correction there. The second modification that we introduced is the suppression of the sensitive attribute and its proxies. So suppression is a very early method for fair machine learning. It simply removes a sensitive attribute based on the idea that if the model doesn't look at the sensitive attribute, it's not going to learn its relationship with the labels. However, we all know that there are other features that may be correlated with the sensitive attribute. The model ends up learning those features as well, which are proxies. So we basically, with this modification, we allow the user to define both if the sensitive attributes or other potentially correlated features are going to be ignored by the ensemble algorithm when it's being trained to calculate the margins. And then lastly, we also define a new margin calculation formula. So the original one was only using the binary predicted values given by the classifiers. We introduced a second margin calculation formula that uses the prediction probabilities instead of the classes. So here we get the probability from each of the classifiers. We take the average probability and then we subtract that to the actual label, and that's how we get the ensemble margin. And we allow for both of these margin formulas to be used in our method.
Regarding the experimental setup, we followed something which was create an IID version of the bank account fraud datasets. To do so, we picked a version of the dataset which has the same size of groups. So we had two groups, if you recall. If you don't, I'm going to explain. We have a group of less than 50, and we have a group of equal or more than 50 in terms of age. And this dataset in specific had the same size of these two groups. And what we did was we shuffled the column of age, and that basically eliminates any relationship between the features and the sensitive attribute and the label also. So and the sensitive attribute, yeah. So we got equal fraud rate, equal feature distribution. Additionally, to have an equal distribution between train and test sets, we chose instances randomly to go to train and instances randomly to go to test. One thing that we note here is that we're gonna tweak a bit the fraud rates because we're gonna inject artificial noise in each group. But we had an original fraud rate of about 1%. And since in like a scenario where we would have label noise, we couldn't make a threshold based on FPR, for example. We did a threshold on alert rate, or on the predicted positive rate, and it was near the alert rate, or near the original fraud rate, or prevalence. Okay, so this data set was perfectly balanced. What we did was we had to destroy this balance with some noise. So let's see how we did it. We had three variants. We have the variant which is more important to this work, which is the blue purplish one, where one of the groups doesn't have any noise. In this case, it's group 0. Doesn't really matter for this analysis, but it's the younger group. And then for group 1, we inject some noise depending on the label. We can randomly flip labels from 0 to 1, from 1 to 0, or from both labels. We also had two other types of noise. One where there was some baseline noise for one of the groups, and then the other would increase, which is the green one, and one where the groups would increase equally with the noise type 1 here in red. It's an appropriate color for when everything is equal. All right, so in terms of metrics, what we have here was we had two groups of metrics. The first for the prediction model that we will get after training on the new data set, and another which is exclusive to methods that try to correct the labels that we had in the data set. So the first two metrics were for the models, TPR, recall, and the demographic parity. This was measured as a ratio. So what we did was we would measure the group which had more predicted positives and the one which had less, and we would divide the one that had less with the one that had more in terms of predicted prevalence for each group. For the reconstruction, what we call reconstruction score, we would check for methods that would change the labels if it got lots of labels correct or not. We also did an analysis on the type of label that we had, if it was a false positive or a false negative, or something like that, to the ones that we corrected. In terms of methods, we tested several methods that were implemented in the Equitas flow package. So the first two were the ones that Inés implemented. We also had one which we call prevalence sampling. And prevalence sampling is basically just random sampling with different rates, depending on the group, to achieve equal prevalence between the groups. So the final result will be something similar to Fair-OBNC, but instead of changing labels, we just remove some samples, some instances. Then we have data repair, which is at the level of the features instead of the sensitive attribute or the label. Here, the features of dataset are transformed in order to match the distribution of the sensitive attributes to the global distribution of the dataset. We have massaging, label massaging, which is kind of similar to Fair-OBNC, but instead of using an ensemble of models, it uses only one model, and it prioritizes the instances which are farther away from the decision boundary of this model to flip them. And then we have the suppression methods, which just try to remove features that are correlated to the sensitive attributes. So the first one is based only on correlation. The second one uses models to check which are a model to predict the sensitive attributes, and we remove the features that are more important to that model that predicts the sensitive attribute until it can no longer predict the sensitive attribute. All right, so in terms of results, what we did was we picked up the data set, we tried to correct the labels, and we obtained this big table. We'll go through it slowly to have some conclusions about it, but we measured that reconstruction score, and we measured the FPR and FNR of each group and the global FPR and FNR for all of the methods that changed the labels. So these were three methods: OBNC, the original one, Fair-OBNC, and massaging. And then here we have different noise rates. We also did this by injecting noise to the label 0, injecting noise to the label 1 only, and injecting noise to both labels. The first thing that we noticed was that Fair-OBNC performed the best in terms of reconstruction of the original labels. Sometimes massaging also performed really well and in line with Fair-OBNC, but the best results that we obtained were always with Fair-OBNC. You can see that highlighted here. Also, regarding the noise, it was something that I didn't mention, but it was always injected in group 1. It was the type 2 injection. So if you recall, it was the violet bluish line where there was no noise injected to group 1. But what we observed was that Fair-OBNC was the method that made the least mistakes in trying to flip labels from this group where it shouldn't flip. So it only had, for example, an FPR of 1% here, and the massaging method, for example, tried to flip always half of the noise rate so that it could meet the halfway point. But with Fair-OBNC, we didn't observe that it was a much lower error FPR rate, for example, here in the case where we only had noise for label 0. Also, in terms of the correction of the group where we had noise injected, we see that Fair-OBNC might not be always the best method, but it produces very close results to label massaging. Okay, so the disclaimer about these results is that we're not presenting the best results for each algorithm, and we are presenting the averages for the hyperparameter optimization stack. And if we presented the best results, we would see much better results in terms of TPR, in terms of fairness, But some bad models will pull these averages down. But we did this considering that there would be label noise in the test set. We did some experiments where we selected the models in a noisy test set or in a clean test set. And we also did this in terms of average, but what we ultimately found out was that it would basically lead to the same conclusions that we do with the averages. And that way there's no problems in saying, oh, you could have label noise in the test set and we would not select the best method there or the best model, not method. And because of that, we decided to go with averages. So in terms of in terms of performance and fairness, we have these two plots. The left one is for fairness and the right one, or the middle one, is for performance. And what we see is that there's really not a lot of difference between all of the models, or in terms of fairness, yes. But we see that for 10% noise rate, Fair-OBNC really is better than all of the other methods. On the rest of the curve, Fair-OBNC is at least as good as the best models in terms of fairness on average. And also in terms of performance, there's a slight decay between some of the algorithms and Fair-OBNC. One thing that we noticed was that also the massaging and data repair methods, not massaging, sorry, data repair methods and the suppression methods really didn't change a lot when compared to not doing any pre-processing or fairness. And also what we can see here is that massaging really goes down in terms of demographic parity with a bit of noise. One thing that we think is the cause of this is that massaging really corrects instances that appear, for example, instances that were originally negative and appear to be positive. Label massaging corrects those instances. And those instances normally then after have a really big scar, and they only belong to the group that had the lower prevalence originally. So what happens is that those instances that are corrected are going to be the only predicted positives in the model downstream tasks. So in terms of demographic parity, everything goes downhill. Okay, so this plot here, it's basically the previous plot where, but with both dimensions being one of the metrics. So we want models to be on the top right, but here we have different noise rates with different markers, and that's an important thing. So we can see that for noise rates that are low, all of the methods except OBNC have good performance and good fairness here in the top right. And then on the noise level 10%, we see that Fair-OBNC is really on a good fairness level. So in terms of the vertical line, it's the one that achieves the best demographic parity, so on the y-axis. But yeah, the second point is on just showing that we have some losses in terms of performance, but we have also some slight increases in terms of fairness. When compared to like model methods from prevalence sampling, no pre-processing at all. Yeah, so these are the general results. And one thing that we also highlight with this plot, which was not really very observable from the others, is that the original method really doesn't produce great results. It adds some things against it. So something that Ricardo also mentioned in terms of the assumptions that it made. But also in terms of like the stopping criterion being very strict on the number of instances that are corrected or achieving no wrong predictions with the ensemble. But yeah, the results are really off with the OBNC. So in terms of conclusions, it's basically just a recap of what we were talking about before. So the goal of this work was to create fairer training data for our models, to create also fairer models. So this is a pre-processing technique. The Fair-OBNC method introduces three modifications to the existing algorithm, which is to have a fairness criteria instead of just selecting instances based on the margin. Having the suppression of the sensitive attributes and proxies as an option for the ensemble, and having the margin calculation based on the residuals instead of just prediction of each of the models in the ensemble. With the benchmark that we did against other preprocessing methods under label noise, we saw that we obtained much better performance and fairness than the original method when having datasets with label noise conditioned on the group and on the label. We have better label reconstruction than other methods of correction, with the OBNC and the massaging method, and the performance and fairness trade-off. It's like one of the Pareto optimal methods for this trade-off. Also with prevalence sampling and performing no pre-processing method at all. Also is the best performance trade-off. So those are basically the conclusions. In terms of future work or in terms of improvements that we can do to this method, it could be also on focusing on one specific type of labels, specifically because of the selective labels issue. So in that case, we only have certainty about a segment of the labels, but not about the other. So that could be an improvement. Also, other improvements could be related to the calibration as you suggested. And yeah, that's basically it. I think that's the those are the future steps. And also having like just correcting one group instead of correcting all of the groups. For the example of COMPAS, it will be like more it will be probably more appropriate to just correct the instances that are from African American and have higher probability of being rejected, though, but where we don't know if they would actually have they would recidivate or not. So that's basically it.
Thanks, everyone.
Thank you.